Okay, so this was quiz 2. Again, if we get broken off, I'm going to continue through the end of class time here, and I'm going to create this video. It's going to have everything we were going to do today in there. So if you're listening along here, don't worry. Don't let me know if I'm lagging. I'm recording it outside of Zoom, so it will be in Camtasia, so it will be good. It'll be a good recording, okay? So the quiz review leads right into everything we're going to finish up with here in the course, okay? All right. So the questions that we had, let me shrink down some Zoom type of things that are sticking in the way here, pop-ups. Okay. So here's the questions we had, just as I've done many times, a dozen times in class. We have some data here, and we had some force. In class we said, what problem should we work on? We talked about these elastic bands that you pull. Okay. So we take all these readings, and I made it long, just to throw it in there that we've been dealing with micro data, little 10 points, 12 points. 1,000 is still small data. When we talk about big data, we're talking about on the order of like billions of records, even millions, if not billions of records. All right. So the first thing I had everybody do was just run the Excel average and the Excel standard deviation. This sets you up with the right numbers, if you were able to do this correctly, okay, for the rest of everything we need to do. Okay, so we just used the formula here for average and the standard deviation, and then we started setting up. Hang on, I just have to move the Zoom window. It's right where I need to look. You can't see it move, but I can. All right, so what we looked at was the distance of every point to the mean. We're setting up for the add map here. Okay, so we're setting up here for the add map. Average distance to the mean of all the points. Okay, now you need to memorize that forever. I mean, I've tried to say it enough times in class that I'm really concerned. I mean, I've spent so much time in statistics where you really have to learn it on your own that I'm trying to offer some special insight into statistics because it's a language of business that, quite frankly, will earn you more money. Okay, because it just shows that you're able to command a view of a problem and apply some math to it. You'll enter into you'll level up. You're leveling up in business if you can do this. So to correctly do the add map, you had to run out the difference of every point to the mean. Okay, so the equation, you had to lock down the C3 value, or else it's going to skip along and get wrong answers. I don't think anybody got that wrong. And correctly, the student followed how we did it in class. We did the sum of the distance, and what do you know? It is 0, okay, because that's our problem. That's why we ended up with the standard deviation rather than the add map, which comes up later. Okay, so the absolute distance, great. So we take the absolute distance, and then we took the sum of the absolute distances so we can get at the average. So we took the sum and divided by 1,000. Yeah, there was 1,000 points there, and it comes out to 0.27. Okay, there's nowhere to draw on here, so I'm going to go to another page. Okay, so what we can do is draw at the beginning and maybe forever. I would always draw these things so you keep an idea of what's going on that's going out here. Okay, so we had an average was what I forget, 5.21. Okay, and we can take a curve, break it into 3 areas on each side, plus and minus 1, plus and minus 2, plus and minus 3 standard deviations. All right, what we calculated was the add map. Use a different color here. Okay, so the add map was point. Let me fix that. 0.27, but the standard deviation. Okay, once we get the standard deviation, all we're doing is we're plotting it down here. We're going out -1 standard, -2 standard, -3 standard, and we look up to where it intercepts the curve. That's all we're doing here. Okay, and it came out to 0.34, I think it was. What was it? 0.34. Okay, so 0.34 is our standard deviation, and we just mark that down. Okay, and you kind of notice as I'm kind of marking it here. Okay, what I'm doing is I'm showing you the z's. Okay, so when we express things in standard deviations, okay, the z this is brought down. I'm just bringing this down here. The Z is centered at 0, and it's delineated in Z's are standard deviations. So I actually talking about it like that right here. But in the raw data, it would be 5.21 minus 0.34. Okay, would be whatever that is, 4.87, I think it is. And if you go up one standard deviation, what is the value of the pull on this exercise band? Okay, so it would be 5.21 plus 34, so it'd be 5.55. Okay, if I have my numbers right there. Okay, so now you've drawn that. Okay, you should have a picture. Always use the picture. It'll keep you from going wrong. Oh, by the way, the student did very well. They got 105 out of 110. Okay. Okay. So we got the first couple of things here. We got the average. We got the standard deviation using Excel. All right. And then what's very important at this point is what specific business meaning does the standard deviation have in this problem? Okay, so this is one area that the student did very well, but had come close, but hadn't actually quite gotten it, so to speak, perfect. But what we would say in a business sense, all right, to our customers is on average, remember this average distance to the mean, on average, the bands measured between what, 4.87 and 5.55. Okay, the standard deviation means the average on average the bands measured between 487 and 555. Okay, to one standard deviation. Okay, and what we would say is that the amount that the bands differed from the mean was about 0.34 pounds of pull. That's, remember, the average distance to the mean. Well, on average, the bands differed. Okay, this is what they differed from the average. Okay, that in business terms, that's what we're talking about. Okay, we're going to see 68% of our bands were acceptable. Okay, if the customer happened to say, I will only take bands between 4.87 and 5.55, I'm only going to take these, we had to cast off, let me find a different color here, we had to cast off everything that was too soft and everything that was too hard, or too, too inelastic. It was too hard to pull here. Okay, so we have an area of A, and we have an area A over here. Okay, so it's 2A, because we're playing around the middle here, symmetric. Okay, everything you do from here on out, if you take data analytics, sometimes I have people in this class taking data analytics. There's none right now, but we go into the next level of statistics with this. Okay, and we learn. You'll see in that class that what I'm showing you here for statistics with this area and the Z's is used over and over. This is the very core of statistics. Okay, so let me just stop there for a sec. First thing, how's everybody hearing me? Any good? Yeah, it's very strange. It's, you talk about variability through the day. It's going, let's apply it to this. We talk about the speed on average for me is low right now. It's like 2.5 megabits per second, and it will be over the period of a day. It'll be bursting way up to 12 megabits per second, and then it drops down to like half a megabit per second. So it's wicked changing on me. It's not just like a slow over the day thing. It's like really fast, abrupt changes. So I don't want to waste air and bandwidth here. Okay, so the second question is, actually this might be for their customers, and this might be an example of a right tail where a lot of my the optimum customers. Okay, so this is the mean. A lot of their customers, I might be lagging here, and I know other areas in my county where they're boosted, they actually are getting really fast, 75 megabits per second right now. They're fidgeting with the network, so I'm just trying to endure it. Okay, so anyway, now as far as questions go, does everybody understand this so far? And I asked that meaningfully. You really need to speak up. Yep, you need to speak up because the rest of the course is going to be built on this. All right, that's why I'm going to review this quiz so carefully. Okay, so we'll come back here. So that's the on average the band pressure or force varies by the standard deviation. It's the average. It's like the average distance to the mean. The reason I ask that question is so do we have the real world feeling for what we're even measuring here? There's so much in the math that we have to come back up for air and say, why do we care? So what? It's legit to go, so what? In any of your classes. Right? Okay. What is the standard deviation like? Okay, so and this is another one I just had to take some points off because I'm not really sure the student probably knew this, but I want to make sure you're writing it and using it. It's average distance to the mean of all the points. It's like. See, that's why I have to put this in here so people don't come out of the course talking ADMAP and nobody in the world knows about what you're talking about. But that's where we start, that's why we end up with the standard deviation. Okay, so the standard deviation is like that. Calculate the ADMAP was done correctly. So we did 0.27. If I went a little bit too quickly through that and you need to know, I guess shoot me an email. All right. But you should be getting that by now. I went over this. I've actually gone over this in much more coverage than I normally do. Okay. Perform the long form. Okay, so that's why I had you do the short form. Just use the formula to make sure that you get the right answer there. Okay, why is the value of standard deviation different than the ADMET? Compare them. Okay. Okay, so what's going to happen is some of the words you want to be looking at is the standard deviation is going to be larger than this intuitive thing that we were talking about, the ADMAP. And that's because, why? That's because the differences are, here's within the equation. I'm not going to write the entire equation here, but you're squaring them. Okay, so you're actually using areas. You're squaring a distance from the point of interest to the mean. Didn't write my little mean thing in there. The distance, we're squaring that, right? So instead of linear, where it goes up like a line, here's 0. Let's go 0. You get something like this. Well, let me think about that. Yeah. So this is the curve. As your x goes bigger, it just goes crazy steep. Finally, as you increase the x this way in either direction, right? That's your curve that you get here, rather than a linear thing that goes off like this, which would be your absolute value. If you took the absolute value, it would look like this. If you take the square, it looks like the other curve. All right. Okay, so that's why standard deviation is always going to be larger than your ADMAP by a little bit. Okay, and why do I keep asking that? So you have a working feel that the actual average distance to the mean it gets boosted. So the sig isn't exactly what we're after. It's a proxy for this concept of ADMAP. People will be slinging the standard deviation around a lot, and by feel and by practice, you just get used to talking about it. But if you don't forget the underlying characteristic of it is like the average distance to the mean of all the points. That's what the world was ever after. Okay. Then the next question says, why do we even need the standard deviation? Why not just the ADMAP? And the accurate answer on why do we even need the standard deviation, why not, it has to do with the fact that we had to that even though we square it, and we always have to keep in mind that it's a contorted ADMAP. Standard deviation is like a contorted, twisted ADMAP. Okay, why do we need the standard deviation? Because we can take the concept. Okay, it's a little view into what math is all about, and it's a number of tools, and you always are using the tool, but you have a hand. This is supposed to be a hand. I'm a terrible drawer here. Okay, so that's a hand. You always keep one hand on the lightning bolt of reality. Okay, a lot of math goes really into the clouds, I would say, right? I have a master's in electrical engineering, but that was mainly math. Okay, and we use I, square root of -1, is another thing. If you've run across this in math and been introduced to the fact that we call the square root of -1 I, does the square root of -1 even exist in the world? No. But we actually use that and leverage that point that It's a tool that gets us some solutions. And when you wind it all the way down to the final solution, all the i's cancel out. It's a construct of math that doesn't exist in the real world. Okay. But mathematically, they can go forward with it and it drops out after a while. Everything cancels, all the i's cancel out. Okay. So that's how you use these imaginary numbers. It's a pure math construct, if I haven't made that point. Okay. So if the average pull force is 521, what is the probability that, let me move it over so everybody can read that. Okay. So this bridges us into today's topic. Okay. If the average pull force is 521, what's the probability between the first question I said was greater than 5.56. Okay, so if we go over here to our picture, what's the probability that we're losing things on the high end? This is when I say lose, we're scrapping. This is scrap. Okay, reject. Okay, excuse me. So how do you do that? Somebody yell at me. Tell me what you do for getting that. How are you supposed to calculate that? Okay. Okay. So if you do the normal distribution of the point of interest is this might not be the right answer for that. Hold on. Let me go back down to 9. Okay. So we know for one thing when you draw it, you know where you're headed. Okay. So when we drew it here, I'm going to kind of reinforce the fact that this is what we're talking about. What's the probability? Let me read the question again. Did I get the question right again? It did say greater than 5. Oh, I'm sorry, I read it backwards. So we were reading that it has less than 4.86. I thought it was the other way around. Sorry. Okay. That's a big deal. Okay. You do this all the time. So we have scrap on both sides, but what I asked was, and I tried to make this question straightforward, okay, is what's the scrap of things that are too weak or soft, everything below 4.86. I'm going to use the dot there. 4.86, okay? What's the area there? That's just a straight up, when we use the norm.dist, it gives us the area up to the point that we feed it, okay? And it turns out to be about 16%. Okay, so we come back over here. 16%, around 16% is the correct area, okay? And then I jumped a level. I didn't go over and I didn't ask what's the probability above 5.5. I pulled another color needed here, so I'll use this. Okay, so what's the area between these? Okay, and I asked a fairly easy, straightforward question. If you understand the geometry of this, it's just 16 and 16 is 32. That would be the scrap area, and then you would just take 100 minus 32 is 68. I'm not using any decimal places here. And what we just determined, by the way, so that the correct answer there was 68%. And what we just determined there, okay, is what has to do with, say, process control. Okay, so here's a 2-minute segue into what we're going to go through right now. Is the way that you use this is either one-tailed or two-tailed. Okay, so when we do process control, before you even saw process control, I was asking you questions here about it. All right, so I was just asking what's the area between here. Okay, so when we talk about process control, we usually learn and discuss even early problems, okay, we discuss it as that some process with a random variable output on it, okay, and we look at this. What we're going to do is the empirical model, okay, of the z distribution here. We call it the empirical model, okay, and you'll use and see this so much that you certainly, And I find this extremely valuable, very applicable to things that you're going to bump into. When you start seeing a problem and you start collecting data on it, you can consider it. It's probably going to be 80% of the time normally distributed in the raw data form, in its native data, native units and whatnot. It's going to probably be maybe a little bit skewed, maybe have a little heteroscedasticity in it, but otherwise it's going to be normally distributed data, right? Okay, so the empirical model is, we already just figured out 1/3 of it. We figured out what is the area between -1 and +1 standard deviation. Okay, so this is +2, this mark here. This is +3. And I'm going to remind you that if you were to be given a normal distribution drawn like this and said, just show me where the -1, 2, 3 and +1, 2, 3 standard deviations end up on this. Okay, if this is it's drawn to ideal data, they fall up on the shoulder, in the middle, and in the tail like that. So it basically looks like that. You're going to get this, it's going to be emblazoned in your retinas when you do this kind of data. Okay, and that's why they call it empirical. It's the walk around. Okay, this makes you join the club of, let's say leveled up business professionals, and you can talk about all this kind of thing. This could be sales, right? This doesn't have to be anything tangible. This could be sales. This could be interest rates, right? Who knows anything about interest rates. There's probably 18 interesting things about interest rates, right? That behave as a normal distribution goes. Okay. How about any questions as I take a little sip of coffee here? Okay, don't be bashful here, okay? Because we're going to need this. Okay, so that's why I want to. You can see why I'm going to review this in a second. Why I'm going over this. And then question 9. Oh, I guess I did ask a question. I asked 16, 16. I forgot I asked it that way. And then the third question in the series here, because it started here. And then we said, what's 1 minus those two areas is basically the 68%. Okay. So what is how do we do the empirical model of this? Okay. Now, this is general. It doesn't even necessarily apply just to this course. We can use this at any 18 different places in a company or more. All right. So why don't we check in to see what that number is for plus and minus 2? All right. And finally for plus and minus 3. Okay. So if we produce something, we will put in production terms. And the middle mark is the average. Okay. So the customer tells us, right? The customer tells us what they're shooting for. Okay. So the average was here, what did we say? 5 point something. What was the average? Let's move over. 5.21. Okay, let's say that the customer wants 5.2. Okay, let's say that's what they want here. They want the average of 5.2. Okay, and we came up with a standard deviation of 0.34. Okay, so I walked through that up here and I showed that 5.21 minus a standard deviation of 0.34 gave us 487-ish, and add it to go the other way is 555. Okay, all right. So let's take a look at what the yield is. Okay, so all of a sudden we change our language into business pros and production. Okay, so the yield is between these 2 points, which the customer gives us. Okay, these 2 points when we're talking about process control are called the lower spec limit. Notice the S in there. Spec comes from the customer, and the upper specification limit. Lower specification limit, upper. They just specify. They say we don't want anything less, we don't want anything more. So we just put words to what we were just using. Okay. Right. So this is one of 2 different ways we're going to use all our statistics knowledge. Right. So what the probability or the yield, the drawing here is the behavior of our process ability. Okay. All right. So what we talk about when we talk about our process ability, we talk about control limits. When we talk about the customer, we talk about spec limits. Our control limits are what we can control. All right. Okay. So this is like the first year we start producing bands. Okay. The first year we start producing bands that we have a lot of variability. Our standard deviation is 0.34. Okay. So in a business term, what should we do next year? I'm asking a question. Somebody answer me this, okay? This is what we can do right now, all right? It says that our standard deviation is equal to 0.34, okay? Is everybody happy that our yield is 68%? Okay, okay. Is 68% acceptable to us? Anybody happy with that? Suppose every band cost us $1 and we sold them for $2, right? So if we make 100 bands, right, we would make $68 for everything in between their spec limit, right? And we would lose $32 in scrap. Get it? Okay. So it cost us what? 32 cost us 68, let's see. Yeah. So we make $1 on the ones that we actually sell. Is everybody happy with this? Right? What's it says 68% is our acceptable level, right? So everybody should be a little bit uneasy that we have such high scrap, okay? What should if I kept if I keep the x-axis constant, what would the curve look like next year if we make an improvement? Okay? So you have to relate what the curve looks like. I'm going to pick some weird color I never use here, okay? So what happens is the next year what we do is our our control curve looks like this, okay? What we need to do is the customer has not moved their spec limits. We have to do more things near the average. And when we take the data for it, we count what the frequency is. We squeeze the curve tighter, but it always has to equal 1. The area of the probability underneath here has to equal 1. So it definitely has to get higher, okay? And this is graphically what we say. Anytime in the past you've ever said, if you play a sport, for instance, I've got to get better at something like basketball, all right? So this looks like the number of shots you make from 15 feet. And the next year, what you want to do is you want to hit it more often. You want a higher likelihood, or actually evidence that you're getting better. This is what you would do. This is data analytics. You'd be plotting this. Okay. So in production, what we have to do is make things tighter to the mean, and more of them near there start coming out. Okay. So I want to give you an idea about how this works. I'm going to quickly go over the empirical model here, which you're highly responsible for. Okay. So if we got 68% here, okay, how did we do that? I'm going to write these things down. I suggest everybody open up an Excel file. I'll wait a minute here. Okay, get yourself an Excel file with a worksheet in there. You're going to submit this as your daily submit here today. And I'll start this by, yeah, any sheet that you've been using that you want to use, you can, or a new one's fine. Just make sure you name it correctly. Okay, so view. And I'm going to zoom in so everybody can see this better. Okay. I'm getting ready to explain. Just get your Excel file open and ready. Okay, so as everybody gets that ready, what you want to do, and your Excel is going to play a trick on you. So what you want to do is we're going to write down three lines anywhere on your sheet, okay? And what I want to write in there is plus and minus 1 standard deviation, all right? But to make it work with Excel, Excel's trying to jump to conclusions here. You're going to see that I put a little apostrophe before that. Okay, that's what happens is Excel was trying to understand what I meant by the plus. It was trying to make that an actual live equation, and it was giving me an error. Okay, so when that happens, you're trying to type text, and Excel's giving you an error because it thinks it's an equation. What you do is you put a little apostrophe, and it'll start interpreting the following stuff as just text. Okay, so what we need is there's 3 levels with the empirical model here. Okay, we want to know what the yield is between plus and minus 1. Okay, I'm putting this row heading here. Plus and minus 2 standard deviations and plus and minus 3. Okay, all right. So by going through this, we get familiar again with it in a different way. All right, and so we're going to recalculate. We already did calculate that 68. How did we get 68? Okay, well, what we said was, I'll draw a little model over here with a sharp pointy pen. Draw with my sharp pointy red. Okay, so what we did is, I'm only going to show half the curve here. Show half the curve. Like this. Okay, so what we did was we took the z of minus 1, so z is equal to minus 1 here, and we looked at the area up to that, and then we multiplied by 2. Okay, then what we're going to do is we're going to show it at minus 2. See where I'm drawing the lines? Remember that minus 1's on the shoulder, minus 2's in the middle, and minus 3 is over on the end. Okay, so we're going to take z minus 2 standard deviations, and we're going to look at the area up to there and multiply it by 2. Okay, and then we take these areas and we subtract it, right? Because we're going to have 2 of these areas on the tail, but we want the part in the middle. Okay, so we're going to figure out the probability for each one of these tails, multiply it by 2, and subtract that from 1. Okay, and then finally, excuse me, got to get a color that contrasts well here. I'll use blue. And finally, we have minus 3. Okay, and what's all we're figuring out is the yields that correspond to plus or minus 1, plus or minus 2, plus or minus 3. Okay, all right, so we're just going to type in here equals norm dot dist. Okay, so for the first one, we're going to use minus 1, okay, is the point of interest. Okay, the mean is 0. Hang on a second here. There's got to be an easier way to do that. It wants the actual native numbers when we do that, okay? So we're going to use the problem set, okay? So we want to know 5.21. You can type this in here. I put a paren in there. 5 minus 0.21 minus 0.34, okay? Was our standard deviation was 0.34. Okay, so the mean was 5.21. Standard deviation was 0.34, and we want true. Okay, now before we go ahead and do anything, does everybody see that? And does it make sense? Will do, yep. The other cheat is you could use your snipping tool and grab a picture of that and drop it into your Excel sheet. I got to watch out for timing. We're coming down to the end of time. All right. Okay, so we need to do one more thing with this, right? We need to, first we have to multiply it by 2, right? And then we have to subtract it from 1. So that's your big equation that you're going to get, and that should come out as 68%. when I hit enter. Okay. Everybody have that? Okay, I hit, and now we have a very precise number. It's not just that rounded 68%. Okay. So what I'm going to do, I'm going to do a little cheat here with you all right? So what you can do is you double click on that, and I want to copy this over 2 times because it's almost the same equation 2 more times, okay? So double click on the solution, but grab the equation, all right? And hit Control C, goes up to your clipboard, and then hit escape. You've got to hit escape or else it blows up on you, all right? And we're just going to drop it in 2 more times here, okay? Right. So to get the plus and minus 2, what we have to do is we have to subtract 2 times the standard deviation. Now we want 2 standard deviations down, okay? Everybody have that? I'll come back to it, okay? So we got the goalposts set by the client, okay? So we have to see what's fitting between the. This is the situation as if their numbers happen to align with plus and minus 2 standard deviations. The yield between there would be 95.45%. Okay. And then finally, when we get down to here, we want 3. Okay. So the tail is going to get smaller here. We're going further and further to the left, so the area up to that point is getting smaller and smaller, right? And it's 99.73. Okay. I'm just copying the numbers over so I can just change the format on them to percent. Okay? Capiche? And we're done. Just upload that for today. Okay? All right. But this is our table that shows graphically what it shows. Draw, pen. Okay? What we did was, I'm going to go down a little bit here. I'll fill that with orange so it sticks out. Okay? Okay, so I'm going to redraw the curve, another ideal curve. What we just figured out, I'll try to make it a little bigger here. Okay. Okay, so we figured out the area between plus and minus 1 is 68. All right. And then when we go out, another standard deviation between here is 95%. 95%. Okay. And then finally, 99.7 is everything from minus 3 to plus 3. Okay. That's what we just figured out. So you can think about this when you're making things as yield. Okay. Here we had 32% loss. Here we had about 5%. And here we had less than 1% loss. And this is the graphical and mathematical approach to how a company does better. Okay. Almost everything can be expressed numerically. Okay. And that, when you say you're getting better at, getting your GPA up, you're working on your GPA. Okay. Basically what you're doing is the rubrics and the rigor and the ranking system and rating system that's calculated, right? You're doing better toward what's expected. Okay, you keep getting better every year. You're getting better and better at this. You've got it now. All of a sudden you've got this college thing down. All right, so you're doing more and more at the level that the rubrics ask for. And with that, just make sure that you upload. Okay, I'm going to type that over here. Okay, so if you can't hear me, hopefully you can read me. Okay, I'm showing down here. We'll finish this up on Friday. Very good. Thank you. You too. Bye. Hang on a second. Let me stop. Hang on just a second. Let me stop recording at that point, all right? Just so we don't have this.